The focus for today is going to be understanding the theory behind doing our functions questions. So we're going to start off with the basics and just make sure we're all on the same page. So things like function notation. Okay, we can have fx equals x squared plus 3. We can have f colon x funny arrow x squared plus 3. These are exactly the same thing. It's just different ways of writing it. The first one is a function of x is x squared plus 3. The second one is f maps x onto x squared plus 3. These are actually exactly the same as saying y equals x squared plus 3. But in this case, we're not assuming a second variable. Okay? We're relating only to x. Okay? In this case here, we're linking two variables. So if we want to be nice and technical, then we're actually better off working with functions and our functions notation. And it's something that moving forward into calculus and even further into trig even, it's going to be things that it's important to bear in mind. Am I working with two variables or am I working only with one variable? So in the same way where you would have a little graph of y against x, now you're going to be working with a little graph of fx against x or gx against x. Okay? The fx is the equivalent as your y. So this is your notation. When it comes to notation, there's a few other things to bear in mind. Whatever you have here in the beginning must be what you have on the right-hand side. So if you've got fx equals x squared plus 3, if you have f of a, you must have a squared plus 3. If you have f of 2, it would be 2 squared plus 3. You must match the right and the left. If you say fx equals 2 squared plus 3, that's wrong, because fx has to have an x on the right-hand side. So as soon as you substitute on the right-hand side, you must have the same thing on your left-hand side. As soon as you change on the left-hand side, you must substitute on the right-hand side. It's one of those basic things, but it's one of those things that really trips people up. So make sure you are precise. Make sure you are very on the ball about what is doing here. So right-hand side and left-hand side must match. Okay, the other thing to bear in mind, as with always, your brackets are important. Substitute values using brackets. So that comes down to the protecting your negative signs. If you have a minus 2 squared or a minus 2 whole square, it's two very different values. And that then affects everything that you do after that. And as you're playing with these things, sometimes at the very beginning of a question, you really, really don't want to make silly little substitution errors, which then knock out lots of marks further on in the question. So take your time to get all of these basics of notation really on the ball, because it's basic, but at the same time, it's got to be precise. Another couple of things, okay? If we wanted to do something like fx equals 11, okay, we can solve for a value of x. Every time we see fx, all we have to do is take the algebra and substitute it for. So fx is still x squared plus 3 equals 11. So x squared equals 8, x equals plus or minus 2 root 2. Remember, we leave insert format unless we're told otherwise. We want to be exact. So whenever you see an fx or a gx or a hx, you can think of that as the function name. Okay? It's just a little thing that's telling you the name. What's on the other side, like the x squared plus 3 or the 2x minus 1, whatever happens on the other side, that's the algebra. And the algebra and the function name, they're both describing the same thing. So you can use either of them. Same like you could use your initials or you could use your full name. It's both still you. Okay, so here we have the fx, the initials, or the x squared plus 3, the algebra. So if we want to be nice and neat, we could say fx equals 11. But if we want to solve, we can't solve name equals 11. We have to have algebra equals 11 to solve. So wherever you see an fx, you can replace with a algebraic statement and then you can solve. So even if you had something like fx equals gx, well, fx we know is x squared plus 3. So let us then create a gx. Let's create him down here. Let's say the gx equals x squared plus 2x minus 1. So if we carry on here, fx is 2x squared plus 3. Our gx is x squared plus 2x minus 1. And again, we've gone from name equals name to algebra equals algebra. And as soon as we have algebra, then we're sorted. We can do things. So we've got our equation. We can move everybody over. So 0 equals x squared minus x squared disappears. 2x. Why are we doing this? We're being silly. We don't want the 0. We want that to be a 4 equals 2x. So x equals 2. So always when you're doing equations, think a step or two ahead and think, where am I heading to and what's the simplest, most efficient route to get there? So that's our functions basics. Okay, we've got our notation. We can translate between names and algebraic statements. Are we happy? Okay, looking good. So let us move on now to talk about what is a function for AS, and then that big bugbear, which is domain and range. So first off, we need to talk about what is a function. So in the lesson for this is a whole entire lesson just on what we're going to talk about for the next few minutes. There's all the different types of mapping. But what we pull out from that lesson is that there's two types of mappings that make a function. They're going to be rather familiar looking. Anything that looks like this is a function. Anything that looks like this is a function, or a quadratic, or a quartic. Okay, so this would be fx, this would be x, this would be fx, this would be x. Now the thing that we've got here is types of mapping. Okay, this one is called a 1, 2, 1, and this one is called a many, 2, 1. The important piece is this 2, 1. Because a function must have a 2, 1. What does that actually mean? What does it boil down to? We're always talking about an x to y. So 1 to 1 means for one value of x, we go to our function and we get one value of y. X to y, 1 to 1. In this case, we have a little bit more fun, okay? Because let's say we go from this value of x, we would have this value of y. But if we came up here also, and if we came up here, we would have the same value of y. So that's why we have many x's giving us one y. So 1 to 1, 1x, 1y, many to 1, many x's to 1y. But what's really important is you only get 1y. That's what gives us a function. Are we happy? You've done functions at IG, and you look at them and they say, x plus 4 is a function. And then you go, oh, x minus 4 is my inverse. Boop, finished. All over. Next. Okay, so when it comes to AS, life is not going to be so glossy and simple. We've got to get into it a bit more. Okay, the first thing we have to do is we have to understand what domain and range are. And this is a sticking point for a lot of people. So please pay attention carefully and please make sure you ask a question if you've got a problem. First off, what is domain and what is range? See how the bottom of domain is all on one line. So we can write him nicely. See how range has a letter that hangs down. So he goes there. So what I'm saying here is your domain is all your x values going into the function. So the domain is what goes into the function. The range is what comes out. So this is all your fx values coming out of the function. Okay, so let us make sure that is absolutely crystal clear. Let's say that fx equals x plus 2. Okay. Let's take a point, x equals 3. Then we would say fx equals 3 plus 2 equals 5. So this one here, he belongs in the domain. He's a value of x. Let us be good students. Fx equals 5. This one here, he's a value of fx. It's a number that came out of the function. So this here is out of our range. So the domain is values that go in, and the range are values that come out. What is really cool is that our range depends on our domain. I see that we have one person who is wide awake. So I'm going to give you a moment for the rest of you to see if you are equally wide awake. There is a glaring error in this last example. Can you spot it? I'm watching the comments. Right, we've got one more person who's come through. Okay, so there it is. We said that what is on the left and the right must be the same. So if we put a 3 in on the right, wow, we don't want to erase everything. We want to go back to a pen. We put a 3 in on the left because we are doing the range that is based on our domain value of 3. So F3 is 5, not fx. Fx is x plus 2. Fx is an algebraic statement. Okay, so obviously I'm half asleep. Hopefully you're now fully awake if you didn't see it already. Remember, mistakes happen. That's why it's important to check your work. It's also important to question your teachers because your teachers are also human. So I hope that we're all happy with the statement that range depends on domain. We shall go back to theory for a while and see if brains manage with theory a little bit better. Okay, we're going to talk about this range and domain interlinking a little bit more. So, range depends on domain. It's a really important statement. What we're saying is that if we have a graph and we draw a line, okay? Let's say that the domain for this is all real numbers. We can put any number into that function and we'll spit out a number. Straight line, perfect, gonna work. What if we took just a piece of that and we said, should be exactly the same line, but it's just that short. So I've had to call it gx now because what I've done is I've restricted my domain. So let's give us some values on our axes. We'll call them A, B, C, and D. So I've restricted my domain. I didn't say x is not any number anymore. Now A is less than or equal to x, which is less than or equal to B. And what we want to do is we want to see what happens to the range. In this first one, if any number goes in, well, any number comes out. So fx is any real number. Here, we're not spitting out any number. We're not spitting out a value of minus 10 from the domain that we've been given. We're only spitting out values between C and D. So C less than or equal to g of x less than or equal to D. So as soon as we crop that domain, we crop the range. We don't have to crop it in 2 points. We could just crop it at 1 point. We could say something like this. So this is now another domain, so it is another function name. Let's say this is E. We can say now that x is greater than or equal to E. Well, we can see then any value here, so any value up to the top we can get, but we can't get anything lower than f. Let's not use f because that's a function vector. Let's use k. So hx is got to be greater than or equal to k, because it can't be anything lower than that because there is no domain to give it values lower than that. Okay, our range depends completely on our domain. So let's look at something a little bit more fun. Okay, straight lines, linear, all very well and good. Are we happy with this concept here that range depends on domain? Okay, we're looking good. So let's look at something not quite so straightforward. Okay, quadratics. Now, this is where we are heading. We are heading away from the safety of linear functions into the much more interesting world of quadratic functions. Okay, so but first we've got to really understand the domain and the range of our quadratic. So starting off with our basic quadratics, we can say that x is an element of any real number. Okay, then we have fx, we have x, we have different colors so we can reuse our function names again. Okay, and here again, x is an element of any real. But now when we did x is an element of any real number for a straight line, then our range was also any real number. When it comes to a quadratic, it's a different story. Because remember, your quadratic only exists for certain values of your range. There are no negative range values for this quadratic. He stops here at A. So here, fx is greater than or equal to A. So even though we can put any value from the domain in, because of the shape of the function, we can only get A's and above out for our range. It's a very similar story when we flip that over and we look at an unhappy quadratic, a minus x squared. Okay? So again, we have this value here, let's call it b. Okay? Doesn't matter, we can put any value of x into this function. But what it's going to spit out is always going to be lower than b. So gx is less than or equal to b. So happy quadratics, our range is always going to be greater than a value. Unhappy quadratics, our range is always going to be less than a value. And that's really important. And I'm hoping now that you are triggering all sorts of things about the importance of that vertex of that quadratic. Because your value of A here is to do with your minimum. Your value of B is to do with your maximum. And that's where it's all tying. It's all hinging on the vertex of that quadratic. The minimum, the maximum, the stationary point. And that is where those reminders to learn completed square format, to really get to grips, to know how to do it backwards, forwards, and in your sleep, this is why. Because your life in quadratic functions revolves around the vertex of the function, and the vertex of your function comes straight out of completed square format. If you have not learned how to complete the square yet, go back, revise it, get it sorted. So let us think of P, x plus q all squared plus r, and let us think of minus P, x plus q all squared plus r. So this first one, we would have a positive x squared, we would have a happy graph. The second one, negative x squared, we would have a very sad graph. Okay, but here, this is minus q r. Remember, vertex always from directly straight out of completed square form. So again, minus q r. Change the sign on the one in the brackets, keep the one outside the brackets. What is so beautiful about this is we've drawn this without any values for q and r. We've drawn this without any axis or any location. But for these quadratics, if x is any real number, then fx is greater than or equal to r. Let's say fx equals, and let's say gx equals, because here we're always going to have gx is less than or equal to r. So it is the value, the y value of the coordinates of our vertex that is always going to give us the range of our quadratic. Now we might want to do something more interesting. We might want to look at a different type of domain restriction, okay? Let's say we have a beautiful quadratic like this, right? But we only want to look at this piece of it here. Okay, so let's call that A. Okay, so we're only looking for this piece here, where x is greater than or equal to A. Now, you're going to have a different one, because now we're not at that vertex anymore, okay? Now we are at the point B. How do you get B, okay? Let's call this one hx. X. So we know that hx is greater than or equal to B. Right, so what is that value of B? Well, what's really funky is, this is calculate from h of A. So what you're going to do is you're going to take your function, okay, the algebraic statement for your hx, You're going to put in your value of A, and it's going to spit out that value at B. And then you know that you're always above B. So being able to sketch your quadratics, okay, and being able to understand what's going on is really important. Let's just make the rest of this quadratic dotty for the moment, because we're not actually using the rest of it, we're just using that one piece. Okay, so what's important is that you understand your quadratic in terms of its vertex, and that you understand if you cut it somewhere else, then you're going to have not that same value of R, but you can calculate it from the quadratic. So obviously we haven't got much into functions, we haven't done composites, and we haven't done inverses, so those will come in the next lesson.